Okay. I believe I'm recording. I wish it would show me if I was.
The top says uh, red.
Okay. Oh, yes. Okay, great. All right. So let's take a look at our syllabus for the course. So, all right. I just get it in the recording. I want you to all to take advantage of my offer to get half of your missed credit on quizzes and exams. Um, I think I think if you all are diligent about that, then nobody will fail. Fingers crossed. Obviously, we can't do that with the final. Well, maybe we can. Let's see. We'll think about that when we get there. Um, let's take a look at the schedule. Oh, shoot. I want to revise the schedule, but I want to revise sort of the end of the class, so just be advised I'm going to change stuff around. We are currently at September 23rd consensus. We're going to talk about consensus today. And we've got our midterm coming up on October 9th. So please be ready. Please don't fall behind on any topics. Now, I thought I'd talk about the homework just a little bit. Um, so I didn't save my work and I did it on the other machine. Okay, I'll just describe to you the problem that I had. So I implemented the Peterson lock, the hierarchical Peterson lock, exactly the way we discussed it in class previously. And then I put it in my tester and it failed utterly. Um, so in particular, what would happen is I would say run on 4 threads, a thousand times increment for each thread, and it would come back with a different number every time for the counter because multiple threads were getting into the critical section. And I racked my brains over this for, I don't know, an hour or so before I finally realized what was happening. It's very subtle, at least to me, right? So you go through and you're getting your locks in order, right? You're getting you get your so if you've got, let me just get a little bit of a visual aid here. Uh okay, so I've got my lock 0, and underneath that I've got lock 1 and 2, right? And so I've got my threads coming in underneath this. 0, 1, 2, 3, right? And all right, so what happens is um, these two threads come in on this Peterson lock, and whoever wins that one gets this Peterson lock. And these two threads come on this Peterson lock, and whoever wins tries to get this Peterson lock. Now, the way I was doing it, right, was I was starting with the thread number. Hey, I was starting with the thread number and I was doing +1/2 to find the parent and then locking. And then so when I went to do the unlock routine, I did it the same way, right? And that was the problem. You have to unlock it in the reverse order that you lock it. You figured that out?
Yeah.
You figured that out? I'm proud of you. Okay. Yeah. What happens is,
I understand. I guess I'm just trying to wonder why it would have to be the first order video.
so what happens is, okay. So let's say this one wins, right? It gets through and it locks all these. And this one is blocked here. right? And the other one is coming through. This one wins, and it gets to here, and it's waiting on lock 0. Now, what happens is if I unlock this lock first, right, then then before this one does the unlock on 0, this one comes in and calls lock on 0. So even though flag is already set, it sets flag, and then it sets itself to the victim, and it starts waiting. Now the unlock method happens, and it sets the flag to 0, and the lock, and it gets in. So it actually breaks the lock because we have two threads contending on coming in as the same ID, trying to do different things.
Yeah, the reason, yeah, exactly.
Yeah. So
Think about it, it's like, imagine you're like herding cattle or something. Like, obviously you want to open up the first guy out, and then let the next two fill in.
Yeah.
That's kind of how I thought about it.
yeah. Anyway, okay. So if any of you figured that out, I'm proud of you. All right.
Looking at the array, you can't easily find the path from the top and the bottom, so what I just did was I took the path from the bottom and then went to the top, saved the path, and then just like.
Yes, that's what I did also, but okay. Okay.
The way that it still did produce a different number, but it was like, say it had 14 cores, it would, each one does 1,000, it would be like 13,980 or something like that. So sometimes it would fill, is that okay?
Well, it shouldn't sometimes fail. I'll have to take a look, but I'm glad you figured out the reverse order thing. So a correctly implemented lock won't ever fail. So we'll take a look. Uh, all right. All right, let's take a look now at chapter 5. Yeah, chapter 5. Okay, so I kind of like this chapter. This is, to me, this is kind of a really interesting one, but we'll see what you think. So we talked about mathematical models of concurrent computation and what is concurrently computable and we haven't paid too much attention to efficiency. And we've talked about weight-free implementations, and that means that every method call completes in a finite number of steps, and it implies no mutual exclusion, right? Because mutual exclusion implies waiting and blocking for steps. A while loop with a yield in it, in particular. And we wanted atomic registers to implement mutual exclusion. So by atomic registers, I just mean sort of regular memory. It's sort of a terminology used in this book. You shouldn't, when you see atomic registers, you shouldn't necessarily think atomic operations, right? You just think like the atomic type, something that's going to be consistently viewed between all threads, right? You either put volatile or atomic on it, right? So we couldn't use mutual exclusion to implement the registers, but we didn't talk about, I skipped chapter 4. That's what that's referring to. Okay, so asynchronous interrupts. So, one processor can swap out, and if it's holding the lock, then everybody is stuck. Or it can be running slower, or it can die. Something can go wrong with it, and it can just stop functioning. And if it's holding the lock, that's the end, right? And we've talked about Amdahl's law and how much it hurts us to have any sequentialized piece of code. So weight-free synchronization might be a good idea in principle, but how do you do it systematically, correctly, or efficiently? So let's think about a queue, right? So we're going to NQ a green ball. We're going to DQ a blue ball. And this is the two-thread weight-free queue that we've seen before, right? So if you've got one NQer and one DQer, magic, it works. But what if you have multiple DQers? So there's a grand challenge to implement a FIFO queue that is weight-free and linearizable from atomic read-write registers with multiple dequeuers. And that's the only aspect that's new there, the multiple dequeuers. But we're not gonna solve that one today. That's just, I want you to start thinking about that one. So while you're ruminating on that grand challenge, we will give you another puzzle, consensus. And this will be important. Consensus says each thread has a private input, say 32, 19, and 21, and they communicate, and then they all agree on one of those values, right? So that's the thing we want to happen. They want everybody to propose and everybody to agree. And so we want to be more formal. We want all the threads to decide the same value, and the common decision value has to be some thread's input. And here's the assertion we're going to make at the start. There is no weight-free implementation of consensus using registers. It cannot be done. No weight. Now, you could do it. You can solve consensus if you use locks or whatever, but there's no weight-free solution to this problem. And we're going to try to convince you of that. They have proofs in the text in various places. And so the proof strategy is we're going to assume otherwise, and we're going to reason about the properties of any such protocol, and then we're going to show it doesn't work. And it's sufficient to show that it doesn't work for a consensus of two threads. So imagine we have some weight-free computation, and either A moves or B moves. And by moves, we mean reads or writes, because that's the only thing you can do with registers, right? You can read them or you can write them. And we have a read-write sort of move tree, right? So with the red thread and the blue thread, and these are all the different possible ways it can go. We start with some initial state, and then we have some final states, and they're either 1 or 0, right? Because we're going to decide on 1 or 0. And we call something bivalent. We call a node in this possibility tree bivalent if 1 or 0 is possible. And we call it univalent if the number's already decided, but maybe we're just figuring out that it's decided, right? So we've got bivalent and univalent. There's one valent that goes to the ones. Okay. So the weight-free computation is a tree, right? Because it's a finite number of instructions. And bivalent states mean the outcome isn't fixed, and univalent states mean the outcome is fixed but may not be known yet. And then there's 1 and 0 valent states which correspond to the various decision values that are possible. So the claim is that some initial state is bivalent, and the outcome depends on chance, the whim of the scheduler, and we can get to an answer. So let's try it. So if both inputs are 0, then all executions must decide 0, including a solo execution by A. And if both inputs are 1, then all executions must decide 1, including a solo execution, right? By B. But what if they're different? Okay. So by way of contradiction, if univalent, all executions must decide on the same value. So, as I say, including these two. So they have to somehow work with solo executions and come up with the same value with these two processors either way. So possible executions include this. This one runs solo and gets a 0, and this one runs solo and gets a 1. So we have critical states and a 0 valent and 1 valent state, right? And so a critical state is a state that on the next move, it's either 0 valent or 1 valent. And so from a critical state, if A goes first, protocol decides 0. And if B goes first, protocol decides 1, right? And eventually there has to be a critical state. So in this example, right, we have a bivalent leading to a bivalent, leading to a bivalent, leading to a bivalent, but eventually it gets to a critical state no matter what we do. If this is going to work at all, right, there has to be a critical state somewhere where we can go from unknown to decided, from undecided to decided. And Okay, so if we could stay bivalent forever, then we wouldn't be weight free, right? Because then we wouldn't have a finite number of steps. So that can't happen. So far, we're fairly general in the way we're trying to prove this. And it could work for all kinds of computation, not just memory like we're thinking about. But anyway, so we have reads or writes to the same or different regions. That's our first concept here. And we're going to look at executions that start from a critical state, and threads cause the state to become univalent by reading or writing to the same or different registers. And we want to end with a finite number of steps. And we're going to show that this leads to a contradiction. So let's say B reads X or B reads Y, okay? Some thread reads, so A runs solo and decides 0, B reads X or Y, A runs solo and eventually decides 1. These states are going to look the same to A, right? So if A runs, so if C is somehow causing this change, A is not going to, is going to see a different number depending on when it runs based on this read. So this doesn't work, right? But it's not really surprising. So it's not really surprising that reads can't cause the critical state to go from one to the other, right? It wouldn't make sense anyway. Nothing's changing if it's just going to be whatever it was to start with, right? All right, so there is no proposing of a value that gets decided on that way. So we know that in these table of possible interactions, the reads are not going to do it for us, but we have the possibility of writes to either the same or different threads. So like if we're writing to the same thread, that's like a flag, and different flags, it's different threads, it's kind of like a CAN protocol, right? But you can't really do this either because the answer I get is going to sort of depend on when I look, and I can't tell looking at the outcome which, if any, which one came first. So if I'm writing to the same, hold on. I'm writing to distinct registers, right? If A writes to Y and B writes to X, you know, it doesn't help me figure out who moved first, right? Because I could look, because if A writes Y and B writes X, then if they look at them, how are they going to know who moved first? How are they going to complete solo, right? It's going to look the same whether one moved first or the other moved first, right? So that can't do it for us. So I thought I fixed these little goobers. Oh well, I missed one. Okay, so this leads to a contradiction when I'm trying to write distinct registers. And if I'm writing the same register, if A writes X and runs solo and decides 0, if B writes X and then A writes X and A runs solo and decides 1, I mean, we're at the same kind of a problem here. At some point, you have to do at some point you have to do a read of the X. So if you write a 0, then you can't really make a decision based on that. So the point is, I could write a 0 and I could look and I could say, oh, there's still a 0 there. I won, right? On the other hand, the other thread could have looked, seen the value was unwritten. You write the 0, it writes a 1. It reads the 1 and it thinks it won. So the one possible execution is we have a null. We have both read the null, and then they write values. And so you can't really tell based on this, you can't really tell writing the same register which went first anyway. So in the end, the states look the same depending on how you try to run it. So what happens is whether we write the same or different registers, we can't do it. And the result, man, I didn't fix the QED. Okay. So the recap is that we can't use these memory registers to do consensus, right? If a protocol exists, it has a bivalent state leading up to a critical state, and the critical state has to be exited by means of a read or a write operation, and we can't devise a read or a write operation that actually takes it out of a critical state. Kind of makes sense, right? All right. So here's a question for you, just sort of to mess with your head a little bit. Suppose I have a timestamp, right? Suppose I write a value and we have like a 64 bit register or something, and A writes a value plus a timestamp in register R1, and B writes value plus a timestamp in R2, and then each reads R1 and R2, and use only the non-blank register or the earliest written. Does it work? No, why not?
Could be in, or they could both write at the exact same time.
So let's consider these possibilities. So let's say that thread A comes first and writes its value and time, and then it checks to see if B has written, and it sees nothing, right? And so it decides it won. Okay. Now A has already written, let's say, so let's say that if in the case of a tie, right, we can do what we did with the bakery algorithm. We can say the thread with the lowest number wins. Okay, so the B writes it there, and then they both look. So uh, so if B writes and then looks, it's going to see that A has an earlier timestamp, right? So it sounds like it's working. Can you give me an execution where it doesn't work? Just think about it in your head. See if you can come up with a way to make it not work. Yes.
So I'm guessing we're assigning the registers to each thread, right? So
They each have their own distinct register, right?
so both of them
Mm-hmm.
register one, thread A's value. Register two is written B's value. They both check, but do the exact same timestamp.
Right. We said we're going to distinguish that by thread ID in that case.
But the thing is, like now both of them.
Right, but you understand. But if they have the same timestamp, then you go with thread 0. Same exact timestamp means you choose thread 0. Is what I'm suggesting. All right. Well, we're assuming we're starting from blank slates. For all these consensus problems, we're going to start with a freshly initialized object that can only be used once. That's another caveat that we're throwing in there. So what's wrong with this? There is something actually wrong with it. And it's kind of tricky because, well, you're probably not questioning the right thing. So what does not exist is an operation that fills in a timestamp and then writes it to memory at the same time. Right? So those are actually distinct steps. So I get the time and fill it in, and then I write it. Those are distinct steps. And so this one could read first, this one the time first, this one could read the time second, and then this one could write the time, check and see this one's not written, it thinks it's when. This one writes, checks the times, it has the earliest one, so it thinks it wins. So it can happen, right? The thing that fools you is when you see this problem written, you somehow think you can get the time, add a value to it, and write it all in one clock cycle. But you can't do that. There is no instruction to do that. I mean, in principle, you could make special hardware that did that, but nobody does. All right. And what would be the point? Just to make this slide work? I mean, I mean, I don't know that it would be too expensive. It's the use case. It's why do I want that, right?
Whole thing revolve around why we want it to work, but it doesn't.
Well, we have a specific problem we're trying to solve, which is consensus, right? And this comes up in a lot of different contexts, right? Like somebody's trying to get a plane ticket or whatever. There's lots of places where a consensus-like problems show up. And you're saying if this is the only way to solve consensus, then wouldn't this be a good thing to make in the hardware? And I grant you that point. There's another way to do it. And we're going to talk about that in some detail. But you're right. That could be something somebody decides, hey, this is the way we're going to make that problem solvable. So what does consensus have to do with concurrent objects? And so, all right, so we have a consensus object that's going to look like this in Java. And it's going to have a decide method, which is going to take a value and it's going to return a value. And it's just, everybody's going to call it at once and they're all going to get the same thing. We consider only one object at a time. Each method can only be used once. And we want something linearizable to a sequential consensus object in which the thread whose input was first decided on completed its method first, is the one that completed its method first. And we're going to define the consensus as an abstract class and implement some methods, and then you can do the rest. So consensus protocol class looks something like this. We have an array that's n threads long of proposed objects. And then in the propose method, what we're going to do is we're going to take the value that I get, take the value that I want to propose, and I'm going to stick it in the array at my ID number, my thread ID number. And then in the decide method, I'm going to figure out which thread won consensus. And then I'm going to look up the correct object from the proposed array using that thread ID. Can a FIFO queue implement consensus? So imagine we have a magic FIFO queue that's wait-free, all right? And what we're going to do with this FIFO queue is we're going to initialize it with a coveted red ball and a dreaded black ball. And the protocol is we're going to write a value to our array, either 0 or 1, depending on what our thread ID is. And then we're going to take the next item from the queue. And if you get the coveted red ball, you win. And if you got the dreaded black ball, you lose and the other guy won. The other thread won. And so it looks something like this. So we have, we instantiate a queue, we enqueue inside the constructor, we enqueue the red and the black ball. And in the decide method, first we propose the value, right? That's the first thing we do. And then we do a dequeue of the ball. And if the ball is red, I return the proposed value at I being my current thread number. And if I get the black ball, I return the proposed value of the other thread. So this is a two-thread consensus protocol. Make sense? So so why does this work? If one gets the red ball, then the other gets the black ball. The winner decides their own value, and the loser can find the winner's value in an array because the threads write to the array before dequeuing from the queue. So it's going to work. And we can solve two-thread consensus using only a two dequeuer queue and some memory registers. And the implication is that that this would give us a consensus protocol from a queue and registers. Assume there exists a queue implementation from atomic registers that is wait-free, and substitution yields a wait-free consensus protocol from atomic registers. So if I had such a queue and it was wait-free, then I would have solved consensus. But we know we can't do that, right? We know that we cannot solve consensus without with just regular memory registers and the requirement of weight free. Therefore, a Q cannot be weight free. It is impossible to implement a 2 to Q or weight free FIFO Q from read write memory. So, it started out with something kind of that may have seemed kind of abstract to you as consensus, and we've shown to you that what it means for a Q, right? Because if you could do this with a Q, that would mean it was this shows you that it's already impossible to do with a Q. All right, consensus number. So an object X has consensus number n if it can be used to solve n-thread consensus. Take any number of instances of X together with memory registers and implement an n-thread consensus. But you can't implement an n+1 thread consensus with an n consensus. That's what we're gonna assert. So atomic, general, just regular read-write memory has consensus number 1. You can solve consensus for 1 thread, if you want to call that solving anything. And for a multi-DQ or FIFO queues, you have to have consensus number at least 2. In order to make that work, you have to have that. So consensus numbers measure synchronization power. If you can implement X from Y and X has consensus number C, then Y has consensus number at least C. Conversely, if X has consensus number C and Y has consensus number D less than C, then there is no way to construct a weight-free implementation of X by Y. So this theorem will be useful to us. And there are certain exceptions that exist that we don't go into. All right. So a snapshot means we write any array element and we read multiple array elements atomically. What about we write multiple array elements atomically and then we scan any array elements? We call this problem multiple assignment. Regular memory registers cannot implement multiple assignment. Weird or what? The single location multi-read-write location is okay, but a multi-location write, multi-location read is impossible. All right. So proof strategy. If we can write to two of three array elements, we can solve 2 consensus. It's impossible with normal memory registers. Therefore, we cannot implement multiple assignment with normal memory registers. So here's how we're going to prove it. We're going to take a 3-element array, and A is going to write atomically to slots 0 and 1, and B is going to write atomically to slots 1 and 2. And any thread can scan any set of locations. So we have an interface like this. We have an assignment, and we're going to assign to index I1 with value 1 and index 2 with value 2. I feel like I'm going to sneeze. There you go. Thanks. And then you have a read of the ith value. So those are the things you can do with this assign to object. And what we're going to do is we're going to start like this. We're going to have a register thread A and thread B. And thread A is going to write to 0 and 1, and thread B is going to write to 1 and 2. And thread A is going to win if thread B didn't move, thread B didn't write its distinct location, or if thread B's value is in the shared value, right? That means that B moved second. So I can check both these locations. This one is empty. This one is empty. A wins. This one has got B's value. A still wins. Okay. On the other hand, if A's value is there, then A lost, or B won, whichever way you want to look at that. Okay, so the way that we do this is here's our code. And we're going to create our assign to object. And then we're going to assign to values I and I+1 with value of I. So if I'm thread 0, I'm going to write memory location 0 and 1. And if I'm thread 1, I'm going to write memory locations 1 and 2. And in both cases, I'm going to write my thread number. Okay. And then I'm going to read the other location. This is the one I didn't write. And I'm going to compute it by saying I plus 2% 3. So if I'm thread 0, this is going to be 2. And if I am thread 1, this is going to be 0. So that little math trick works out. So if the other is empty, or the other is my value, then or the other if the other is the other's value, then I win. Otherwise, the other thread moved and I lose. Okay, so I can solve consensus. So if a thread can assign atomically to 2 out of 3 array locations, then we can solve 2 consensus. Therefore, no weight-free multi-assignment is possible from regular memory registers. So now we're going to go back to something that we have talked about, read, modify, write objects. These are atomic operations like, increment, you get an increment, compare and set, so on. So a read, modify, write object looks something like this. We have a class RMW register, we have some initial value, and then we have some method. If you want to think about this in Java implementation, you can call it a synchronized method. And we're going to have get and mumble. Mumble is this in these slides in this book that they like to use mumble as a whatever, a thingamabob. So we're going to do a get and mumble, and we're going to get the prior value. Then we're going to mumble the current value and get a new value, and then return the prior value. So that's how that is going to work. All right, so most synchronization instructions are RMW instructions, read, modify, write instructions. The rest can be trivially transformed into RMW methods. So, okay, so we have a read. This is not going to modify anything. This is just a read, but it's put into this same framework, right? So f of v equals v. And then we're going to have a get and set. So a get and set is going to put a new value in and return the old value, but it's going to do it atomically. So this is, we're putting the new value in there like that. Then we have a get and increment, right, where we have the prior value, but this time this dot value is going to be value plus 1. We have get and add, which is like, get an increment, except we're adding something other than 1. And then we have compare and set, which is going to say if we have the expected value, then we update it to the updated value and return true. Otherwise, we return false. And so the read, modify, write looks kind of like mumble looks kind of like this code here with something special in place of mumble. And so a read, modify, write method with a function mumble is non-trivial if there exists a v such that v does not equal mumble. So anything that changes the value is going to be something non-trivial. So not read. So identity is trivial. Get an increment is non-trivial. All right. Any non-trivial read, modify, write object has consensus number at least 2. So that's good. No weight-free implementation of RMW registers is possible from regular memory. I just say regular memory whenever I see atomic registers. Hardware RMW instructions are not just a convenience, right? So these special instructions that we have on our hardware are there for a good reason. A subclass of consensus, we have the propose method, which just stores something in an array, and a decide method. This all subclasses are going to have this. Okay, so here's the proof that any non-trivial mumble is going to give us 2. We can initialize our register. We can call this to see if it's first, get and mumble. If we have the original value, then we're first. And if we do, we use our value. Otherwise, we use the other thread's value. The end. Pretty simple, huh? All right. Okay, so we have displayed a two-thread consensus protocol using any trivial RMW object. Let me pause here for a minute. So how much sense is this making to everybody? Do you have somebody must have a question? Tristan is unsure. Very.
Question.
Yeah, I feel like I'm like a 7 out of 10 right now. That's all I can say.
All right. Well, let me ask you this. Let me ask you guys a question. So we've seen that we can solve two-thread consensus by writing to two memory locations out of three, right? And you know how that works. Could you repeat that logic if I asked you to? Barrett?
Right?
Okay.
Well, actually, I can't repeat the whole logic, but I know that you can't do it for a normal register because you have one, you take it or lose it. You have no more information about possibly gleaning who could have written first. But the array of three, because you have the two extra memory locations there for the threads, you can get a better sense of what was there first. It's kind of vague.
Okay.
I just know that that's pretty much what I got. I just know that the rule is, let's see.
So think about this, right? Try and reconstruct it in your head. How do I do two consensus from writing two out of three memory locations? What did we do? What did thread A do? It wrote to 0 and 1. And what did thread B do? Wrote to 1 and 2. Now, how does thread A know if it won? Well, okay, somebody raised their hand.
Take up less spaces because B overwrote the one in the middle.
Take up less
But
spaces.
like, if you're looking at the three spaces. Right?
Yeah,
If A wrote first, then B will have two of the spaces because it overwrote the one.
right. Unless B didn't write, in which case,
The one on the end would be empty.
right. And that's all there is to the algorithm, right? You guys have just told me how it works.
Why do we need consensus? Like, what are we aiming for?
Mine has the same.
So let's rewind. Okay, at the start of the class, we were talking about wait-free protocol, right? And we were saying, why is it that we want a wait-free protocol? And the problem is because when we use locks or other non-wait-free things, then it means that one thread slowing down or stopping can bring our whole computation to a halt, right? And or make it sequential or some awful thing. And you all saw how destructive Amdahl's law is, right? You automatically lose even a tiny fraction of code that's sequential means that you're very limited on how much you can speed up. So the idea is we want to figure out how to do things in a way that's wait-free as often as possible. Now, we can't always do things that way, but we want to do it when we can, usually, right? Because we want to avoid these situations that we've described where we lose performance. So what we did was we started with a simple problem. So whenever you try to analyze anything, right, your goal should always be try to make the problem as simple as possible. The less extraneous, confusing things you've got in the problem, the more clearly you can reason about it. And consensus is just a sort of an example of a simple thing, right? Everybody proposes a value, somebody wins, right? It's not computing the integral of the error function or anything. It's something that's relatively straightforward, right? So that's why we did that. And so now we're trying to work through the implications of what we learned. So we learned that we can't do consensus without some kind of read, modify, write instruction. And we've learned that we can't build that wait-free queue without this read, modify, write instruction. And we can't do simultaneous write to multiple locations without some kind of special hardware support, right? We know we can't, we have, starting with that problem of consensus, we're getting a bigger, gradually getting a clearer picture of what we can and can't do with the tools we have. And we're also getting a picture of what kind of tools we'd like to have or need. So getting the timestamp and writing the memory at once would be kind of a read, modify, write instruction that we could implement. Nobody does it, but there's lots of other ones that they do. All right, so
Ways that we solve the problem, but we don't have the either writing to locations or.
right. So part of this is it's a history lesson, right? When they first started making computers, they didn't realize they needed read, modify, write instructions. And so we built Peterson locks and filter locks and bakery locks in an attempt to solve synchronization on multiprocessors. But we realized that this is very limiting, right? And remember how memory intensive and resource intensive filter and bakery locks are, right? You know, when I have 100 threads, you need 100 flags and 100, victim things. And, it's just crazy, right? But with read, modify, write instructions, we'll be able to do much better, and you'll see that. And so part of this is leading you through the history of how we learned how to compute, right? And how we came to realize that we needed special instructions in the hardware for synchronization. Yes, Ryan.
So if they just designed computers in the first place with all this in mind, would we not have locks?
No, we still need locks for some problems. There's some problems that, it's like, okay, so the single reader, single writer queue, you don't need locks for that, right? It's wonderful. But when you have more, and there's other special cases, we're going to have two dequeuers and an enqueuer, and we can figure out a way not to have locks for that. But for general queues, you pretty much do. There's just lots of problems. And then there's also an issue of complexity, right? So some of these algorithms with atomics can get very complex and tricky to figure out. And think back to our discussion of linearization, right? We want to be able to understand how methods linearize. We don't want to have to think about the instructions that are happening inside a function call and what order they're happening in and how that order is affecting our calculation, right? Because if we do that, we'll go insane. Everything will get too complicated. And a lot of times when you're doing these atomic things, because you don't have a lock, you're doing one atomic instruction after another, you have to do that harder reasoning. So a lot of times, if you're trying to solve a problem, the level of complexity is just going to be so much less if you use a lock. But even if you're using locks, it's going to turn out that you're going to want these read, modify, write instructions. You're not going to want to use filter locks. They're not the most efficient thing possible. Okay. Does that help us with our sense of purpose?
W is going to help better.
It's going to help us build better locks, and it's going to help us write faster code. And this is how we realized that we need it. This is why we need it. All right.
Use RMW without locks.
You can. And there are certain circumstances where that's the right thing to do. Okay. So let F be, so we're thinking about various, so here we're thinking about various synchronization mechanisms, and we said any non-trivial one is going to give us consensus number 2, right? But we probably want something better than consensus number 2. So we have displayed a 2-thread consensus protocol using any non-trivial RMW object. And we can say that, and now we're going to look at interfering RMW. So let F be a set of functions such that all Fi and Fj are either commute or overwrite each other. So what are instructions that commute? Plus. So get an increment, right? Get an increment is gonna be something that commutes. And overwrite, well, that's get and set, right? But things, what are other things that commute? Multiplication. So get and multiply by 2. If I had such a thing, and I think some hardware does have such an instruction, right? That's going to be something that commutes. And the claim here is that any set of RMW objects that commutes or overwrite has consensus number exactly 2. So like these first processors, when they said, hey, we need RMW instructions. And so they put get an increment in there. Guess what? You can only solve consensus 2 with that. Right? It turns out. So test and set, swap, get and set, fetch and increment, right? All these things are going to be consensus number 2. So if we're going to go back and look at our critical state, we're going to have A applies F of A, B applies F of B, and C runs solo. So we're going to have a third thread that's trying to distinguish these things, right? And if they're going to run, so the point is a third thread, if we have A and B applied and they commute, then thread C can't tell which of them ran first because it's got the same value. If both of them call get an increment, okay, it's 2, so 2 threads ran. What can I do with that? So that's part of the problem. Maybe the method's overwrite. So in this case, it's fine, right? I wrote F of A and I get a 0. But in this case, it's not fine because B wrote first, but all I see is what A did. And so C can't tell that B should have won consensus. So if I overwrite or if I commute, then I can only solve consensus 2. Yes, Barrett.
Didn't quite understand that.
So I've got 3 threads. I want to see if I can solve consensus 3. All right. So in that case, what has to happen, if A and B move first and C runs third, right? C has to be able to look at something and tell whether A won or B won. Otherwise, I can't solve consensus, right? And if I overwrite, then C can't do it, right? Because if I overwrite the same location, so if B writes here and then A writes, all I can tell is that A wrote because it overwrote it, right? I have no record, I have no remnant of what B did that I can identify to tell me that B should have won consensus, right?
So the information is lost because A over.
Yes,
You can't.
right. So A knows that it won because it did a get and set and it found the old value. I mean, A knows that B won, rather, right? In this case, A knows that B won because it's got a get and set.
This is like the array. B wrote first, but since the other blank wasn't empty, A still knows it won, even though it overwrote.
Yeah, because it can see the old value because get and set returns the old value.
The get would be like I returned the red square or something. And
Yeah.
put the blue square down. But I still have the red square in memory, so I'm working with that.
Right, but C can only see the memory location after A is done with it. And it can't tell that B ever did anything. So that doesn't work. And likewise, if it commutes, right? If it commutes, C can't tell which of these 2 ran first. They can each tell, right? They each know. But C, that's running third, it can't see. I mean, because let's say that we have F of A increments by 1 and F of B increments by 2, right? Either execution of this leads to the thing getting incremented by 3. And how do you know which one? Which went first, A or B? You don't know, right?
If they didn't commute, there would be some kind of order to the.
Right. So what's going to happen is if they don't commute, if you have something that doesn't commute, right? Then you have the possibility, then you're probably guaranteed at least consensus number 3. Because if it doesn't commute, you can engineer values such that you can C can tell which one moved. You could just generally consider it true that if you've got something that an RMW operation that does not commute, then you have 3 or more. You don't know. Maybe it's 4, maybe it's 5, maybe some other number. Oh, I have allergies. I don't know if you knew that. And this morning I said, hey, I think I can get away without a Zyrtec today. Okay, many early machines provided these weak RMW instructions: the test and set, the fetch and add, the swap. We now understand the limitations of these instructions. But why do we want consensus anyway? Well, we've sort of talked about that. But let's look at the compare and set operation. So we have expected, and we replace the value if it's what we expected. Compare and set has infinite consensus number. So think about this, right? We have an atomic register, and we initialize it to -1, right? And now we do a compare and set from -1 to our thread ID. And now we return the value in the proposed array. That's it. That can work for any number of threads, because only one thread will succeed in doing that compare and set. However many call, right? Only one will succeed. Only one will see a -1. And that's the way it works. So if you have a compare and set, you have infinite consensus number. And so it becomes the most important synchronization instruction on the CPU when it's there. Yes, right.
So why does only one thread end up seeing the minus?
Because let's say thread 0 moves first. It sees a -1, so it overwrites it with a 0, right? That's what compare and set does. It sets when it sees the value it expects. Now the next thread comes in. Let's say it's thread 85. Thread 85, it sees a 0, right? So whichever thread goes first, it's no longer -1. It's that thread number. All right. So we have our consensus hierarchy. We have our regular memory, which is consensus 1. We have consensus 2, which is get and set and get an increment. And then we haven't found anything with different numbers, but we have infinity for compare and set. Yes, Tristan.
So, in my words, like, it will like, only set the value that knows what it's expected. What happens if it doesn't do that? What happens if we get a value that we
It does nothing.
expect? It just does nothing.
Yeah.
When will it be right? I guess it like,
It can only write if it sees the value it expects.
yeah, so like, say if we want to use the same memory multiple times, is that like something that we care about?
Well, we could do that. We could do that. But first point is compare and set does not commute, right? So that's one of the things in its favor. It does not commute. And that's part of the reason why it gets us to infinity.
So we'll only use compare and set if like we're trying to decide something but not like.
There's a lot of different ways and a lot of different algorithms to use compare and set. This is why it's infinity. We're saying we've got this example program as proof that it's got infinite consensus, or at least as big as an integer, right? Now, strangely enough, many modern CPUs don't have this instruction. What they have instead is they have a different thing that's equivalent. They have load exclusive, store exclusive. So what they have is they have a register that you can read it, but then when you go to write it, the write will fail if any other write has happened by any other thread. So it kind of if you have that read exclusive, store exclusive, you can build compare and set out of that, and likewise you can build one from the other. But for whatever reason, at the lowest level of hardware, the load exclusive, store exclusive seems to be the favorite thing. And I'm not sure why. People who design hardware have their own considerations, I guess. But it was very surprising to me when I found that out. even regardless of that, though, because the compare and set instruction is in all the atomic libraries, they have to build the compare and set instruction from those other primitives in order to make any like standard program work. But that's just the way it is. Any questions? Are you feeling excited about infinite consensus?
Consensus, like,
Well, this is how we use it to solve consensus. So
we're gonna use.
how are we going to use this? Well, we're going to have a number of different uses for it, but it's kind of interesting, you know. You as computer scientists, right? You learn about the Turing machine, right? You've got this head that moves on a tape, right? It can read and write instructions, but it can only read or write instructions. The Turing machine description doesn't have a read, modify, write concept in it, and so the Turing machine can't really solve a consensus. Right? You need this one augmentation to the Turing machine to solve consensus. So that's kind of an interesting thing about parallelism. All right. Multiple assignment. Okay, so here's a thought for you. We had that multiple assignment. We wrote 2 out of 3 locations to solve 2 consensus. Can you think of a way to solve 3 consensus with if you had this ability to simultaneously write memory locations, could you solve 3 consensus? So clue, you gotta think more things, right? Instead of 2 out of 3, you got to do something more. Let's just focus on 3 consensus. Let's see if we can figure that out.
Is it very obvious? Should it be coming to us?
One person at a time, please. Reagan. Yes, it actually does. But so the idea is we need. So think about the way this works, right? We need one location. When we did the 2 consensus, each thread had one location that only it wrote, right? So that we could look at that location and we could tell whether that thread moved. And then we had a location that they both wrote, and we could look at that location and we could tell which of those threads had moved last, right? Because its value would be there. Now, suppose we have 3 threads. What we're going to need is we're going to need one unique location for each one of them, right? And for each pair of them, we're going to need a location. So the idea is if I have 3 threads, I don't know what I was writing there. Okay, so if I have 3 threads, I'm going to have 0, 1, and 2 are my threads. Thread 0, let's say, is going to write to its own special location, which will be 0, and it will write something. It'll write, and thread 1 will write to 1, say, and thread 2 will write to 2. But then each of these will also write to 3, right? And each of these will also write to 4. And then each of these will write to 5. Okay, so now I need 6 locations to do this. And so now I can do the following. I can have 6 locations all initialized to null. Thread 0 can move, and it can write 0, 3, and 5, right? And it can look at thread location 1, and if it sees a null, it knows thread 1 didn't move. So it knows it beat thread 1. And then it can look at location 2, and if thread 2 is null, then it knows it also beat thread 2, so it knows it won consensus. Let's suppose now that thread 0 moves and then thread 1 moves after it. Now thread 0 is trying to assess whether it won. It looks at thread 1, it looks at location 1, and it says, oh, thread 1 moved. So how do I know whether I beat thread 1? Well, both thread 1 and thread 0 write thread 3, right? Location 3, rather. So I go and I look in location 3. If location 3 has a 1 in it, then thread 0 won. If it has a 0 in it, then thread 1 won, because the one that moved last is the one whose value is there, right? And then if I go on to look at 2, then I know that I've beaten the other 2 again. So that works. So that's how we can do it. We can go step by step. If we have multi-assignment, we can go step by step through these bits to determine for each thread, did we beat that thread? And you know, let's say thread 1 moved first, then thread 2 moved, then thread 0. Let's say it's that way. And thread 0 is trying to determine who won. So first it determines that all 3 have moved. And now it's going to say, did I win compared to thread 1? And the answer is going to be no, right? Because a 0 is going to be in location 3. So it's going to say, okay, now my candidate is 1. Did 1 win or did 2 win? And so which does 1 and 2 write? So it can look at memory location 4. And when it looks at memory location 4, it's going to see a 2, and it's going to say, okay, thread 1 won. I will use the proposed value at location 1. Make sense? So I need to have, in order to solve consensus with multi-assignment, I need K memory locations. I said bits, but you know, whatever. We need 1 memory location for each thread, and then 1 for each pair of threads. And so that's K, and that's K times K minus 1 over 2 is the number of pairs of threads. And if we add those 2 things together, we get K times K plus 1 over 2. So you can solve K consensus by writing K values into K times K plus 1 over 2 memory locations. Does that hurt your head? No? You actually got that one. Yes.
Example, if you ever look at spot 5.
All right, so spot 5. Oh, I'm sorry, I did it wrong. Hold on. This should be blank. Okay, so if I'm trying to decide whether thread 0 or thread 2 won is when I look at 5. Right? It's supposed to be for each pair. I don't know why I put it 3 times in there. Just, you know, human beings need error correction. We're like AI, we hallucinate. Kendrick, does this make sense to you? Well, then you should stop me and ask me questions. So can you, yes, Barron.
Well, if you're about to ask them a question,
No, let's hear what you have. As long as you get your hand raised, you might forget.
a similar vein, I was just gonna go through the example, just make sure you compare among all of the bits, and then you compare the pairs, and then it was going left to right, so that's why you had 2 here and 2 there, and 2 for the final.
Yeah, that's right. I just wanted to show that each pair had a value to a memory location that it wrote. Calvin.
Going by A is equal to 3 on the left-hand side of the equation. I calculated a 4.5 or 9 divided by 2.
So if we're trying to solve K, if we have tried to do K assignment, so assigned to 3 values, 3 times 4 over 2 is 6, right? Okay. So that's what we had over here. Right? That we got 6 locations, 0 through 5. Is that
I think I would put them on the left side of the equation. Where there's an addition.
here, you mean?
Yeah.
Right. So what I'm saying is k plus k times k minus 1 over 2 is equal to k times k plus 1 over 2. That's just straightforward algebra. You see that? Make sense to everybody? So if you wanted to solve consensus with 3 memory locations, Kendrick, could you do it? So if I have thread A and thread B, and I'm writing, or thread 0 and thread 1, I'm writing 0, 1, and 2. Which one does thread 0 write? We have 3 locations, 0, 1, and 2. We have thread 0 and thread 1. Which locations does thread 0 write? It writes 2 of them, right? So let's go back. How far back do I go?
So each
I can't.
thread will write.
Yeah, here we go. Yeah, right. So thread A writes which ones? Right. And thread B. And so how do we know which one won consensus?
B, well,
So how do we know if A won?
0.
So A wins. A wins if
If there's nothing at 2, then A wins.
Mhm.
We know we did it right. And
on the other hand,
if B overwrites A, then A wins because.
at location 1, right? The common locations. They each have their own location they write, and they have a common location that they write, and that's how that works.
So what would be the win cases for B again?
B wins if 0 doesn't get written, or if 1 is written with A's value. You see? So if 0 doesn't get written, that means that A didn't write. But if A's value is in 1, that meant that A moved last. And therefore wrote B.
So when you scale up for 3, it's the same thing, but
It's the same thing, but with more memory locations, right? We have one location for each pair, and then one for each to write their own value. All right. Where was I? Does anybody remember the number? All right, let's see if that looks okay. Yes, that looks good. All right. Lock freedom is an infinite execution. In an infinite execution, infinitely often, some method called finishes. And this is like one step above wait free, right? And so this is the pair of them. And any wait free implementation is lock free. And lock free is to wait free. Lock free is the same as wait free if the execution is finite. Old saying, lock free is to wait free as deadlock free is to starvation free, which I think you can understand from that table, right? It's a question of fairness. Lock-free consensus is as impossible / difficult as wait-free consensus. And all the results we presented hold for lock-free algorithms also. Universality, who cares about that? Oh, and I have to think about whether I want those to be your homeworks. That's what I've decided in the past, but I want to look at them and think about it. But I can't tell you how happy I am that there are people in this class that figured out that you had to unlock the Peterson locks backwards. Well, but I'm glad that you, number one, realized it wasn't working, and number two, figured out how to fix it. That just makes me so happy. Okay. All right. I think that brings us to the end of the material for today. Are there questions? Kendrick.
So I know we solved it for 3, but it basically would just keep scaling the more threads.
That's right. You could do the same thing for 4 or 5 or 107. You just need a lot of memory. Yeah. All right. I think consensus is really cool, right? I think it gives you a lot of insight into the read, modify, write instructions and why they are what they are. Yes. So what we're going to do on any modern infrastructure is we're going to build locks out of read, modify, write instructions, and they'll be far more efficient than the filter and bakery locks. But the fundamental thing that's different about locks and this is weight freedom, right? Locks are not weight free. By definition, they are not weight free. So, and we talked about weight free as an important consideration because of Amdahl's law and because we want things to go as fast as we can, you know. So those are the steps that link everything. But it's a key thing about consensus problem. If I don't, and this is like a kind of thing I can ask you, right? Why can't I solve consensus with locks? What?
Sorry, there's no real tension there. It's just one guy goes and it's completely done.
What if I use a Peterson lock to solve 2 consensus? Why can't I do that? Why can't I use a Peterson lock to solve 2 consensus? 2 threads.
One of them can go on forever.
Yes, and part of the definition of the problem is weight free, right? I said the consensus problem, part of the definition of the problem is that it's supposed to be weight free. And a Peterson lock is by definition not weight free. All right.
That's the loop.
One has to loop and maybe deadlock or who knows what else. Okay. All right. Thank you for your attention.